Hi, we are Team Rock Raiders, a multidisciplinary engineering team from Rensselaer Polytechnic Institute. This is our first year competing in the Mars Rover Challenge. Our goal is to design and build a rover that completes various servicing tasks in a desert-like environment.
The mechanical team is concerned with the design and fabrication of the rover's main structures. This includes the chassis, drivetrain, and manipulator. The chassis is constructed from 6061 aluminum, with loads distributed along its internal ribs and outer skin. By slotting together the 1/16 inch sheet metal, the chassis can be made both light and highly rigid, while maintaining a large internal space. This internal space is used to house the rover's electronic components, such as the battery and motherboard, as well as any instruments for the science tasks. The rover will be required to traverse difficult desert terrain. To provide stable travel, the drivetrain uses 6 carbon fiber wheels with independent suspension. The rover's primary manipulator is constructed from the same aluminum as the chassis. Precise motion control is provided by linear actuators. While fabrication of the chassis is underway, subsystem development is supported through a functional testbed. For the time being, this testbed provides a serviceable platform through which a majority of the rover's final systems can be tested. Successful trials of critical electronics and software components have been conducted using this testbed.
The electrical subteam deals with creating a safe power distribution system to handle the load of the rover. The rover uses an 80 amp-hour lithium-ion battery with a 100 amp circuit breaker and emergency stop in series to prevent current spikes from damaging connected electronics. The current then goes into a parallel distribution system, which leads into the drive system, the communication system, the motherboard, and sensor array. Each connection is fused for the current of that particular load. All motors are controlled via roboclaw motor drivers, which receive 12 volts from the power distribution system and can control 2 motors each. The roboclaws are controlled via serial communication with the motherboard, which allows for complete control of the motors. They can also handle encoder feedback, which allows for a closed-loop control system. The wireless communication system utilizes 2 Ubiquiti 900 MHz base stations to form a point-to-point transparent bridge. The bridge allows for bidirectional communication, and the 900 MHz bandwidth allows for a high data transfer rate and better penetration through solid surfaces.
The software is built on the ROS framework. This makes it easy to communicate between the base station and rover, as well as do modular coding, reuse code, build GUIs, and use existing robotics software. For driving and navigation, we have a rover from the team's previous experience in the NASA Sample Return Robot Challenge to use as a test bed while manufacturing the final rover. This allows us to test sensors, code, and practice operating the robot. We also have a robot arm with a similar kinematic structure to our designs. We can use this as a test bed for arm control. We intend to use inverse kinematics to simplify operator control. This testbed allows us to test and practice with our code while the arm is being manufactured.
The goal of the science team is to acquire and test samples from the field to determine the likelihood of the soil supporting microbial life by comparing the conditions of the samples to the conditions necessary for supporting extremophile microbes found on Earth. These environmental conditions include the presence of water, as well as temperature and pH. In addition to current conditions, geographic data will be used to determine if liquid water was present in historic conditions, if not present currently. The instruments we intend to use to acquire the necessary data include a thermoprobe, moisture probe, wide-angle panoramic camera, and microscope. More specifically, the microscope will tell us information regarding weathering and sorting of soil grains, giving us a clue into past geologic processes involving liquid water. The moisture and temperature probes will allow us to collect basic data regarding present capabilities to support sustained life. Information gathered from the wide-angle panorama will aid in the selection of a testing site that will most probably contain evidence of water.